One user query can bury your search API in nested ORs and leading wildcards. Lark turns it into an AST you can validate and reject before retrieval. You'll learn how the pieces fit into a workflow that turns search text into a check tree and rejects unsafe patterns. I'm Professor Pi, teaching search and IR with simple Python. Search boxes are wonderful for users and a headache for backends. A few ORs or an aggressive wildcard can instantly blow up matches and spike latency. So, instead of hoping for good input, we parse and validate before we hit the index. Lark is a compact parser library that turns free text into a structured tree. Once it's a tree, we can count clauses, measure depth, and score wildcard risk, all before any retrieval runs. That gives you simple, automatable rules to keep the search system predictable. The core move is straightforward. Turn the string into a tree, walk it, and reject the patterns that would be expensive. You want to allow exact phrases, controlled Boolean logic, and light wildcard use, and deny deeply nested or wildcard-heavy queries. This approach is transparent. You can point to the exact node that triggered a rejection. The trade-off is obvious. Strict limits can annoy power users, so tune thresholds with care. We will build a tiny pipeline that demonstrates this idea end to end. It parses a Boolean-style search language, maps the parse tree into a compact allow-listed AST, computes simple complexity metrics, and then gates retrieval based on those metrics. The code is focused on concepts, so it reads cleanly and maps directly to real checks you can add to your search layer. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we start by defining the smallest grammar and parsing a single string to a tree so we can inspect it. This snippet defines the smallest Lark grammar for a Boolean search query. A user query can be syntactically meaningful to your search backend, while still being dangerous later. So we first make the accepted language explicit. The grammar allow lists words, parentheses, and, or, not, and wildcard characters inside word. Then, Lark grammar parser equals LARR builds the parser, and parser tark parse turns one query into a structured tree instead of loose text. The visible output shows the parsed root and child count, proving the query is now inspectable before retrieval. We parse successfully, but the parse tree contains more detail than we want for policy checks. Next, we'll collapse that shape into a predictable internal form that only expresses the primitives we actually enforce. This example converts the Lark parse tree into a compact allow-listed AST. Search systems usually need a stable internal shape. Not every grammar detail Lark keeps for parsing. To-AST uses Lark's transformer to map only known primitives into tuples: word, not, and or. The fold helper keeps single-child groups from adding noise, while multi-child Boolean groups become explicit AST nodes. That makes later validation predictable because every node kind is one you intentionally support. The visible output shows the top-level operator and how many items it controls, which confirms the query is ready for policy checks. With that compact AST, we can actually measure structural cost rather than guessing from raw text. The next snippet shows a simple scoring function. This snippet measures the AST produced from the Lark-backed query parser. The painful failure mode is not just bad syntax. It is a valid query that expands too much or nests too deeply. Metrics walks the AST recursively and returns 3 values: clause count, maximum depth, and a simple wildcard cost. The wildcard scoring is intentionally small and visible, with star costing more than question mark, because prefix or infix expansion can be more expensive in many search backends. Raising that weight rejects more wildcard-heavy queries. Lowering it allows more user flexibility. The visible output shows the actual complexity signals you can enforce before search runs. Once we can score a single query, it's useful to compare a set of candidates and pick the cheapest, safe form. This snippet compares several Lark parsed search queries using the same AST metrics. In retrieval systems, query rewrites, UI filters, and user-entered strings often compete for the same backend budget. The loop parses each text with parser.parse, converts it through to AST, and calculates clauses, depth, and wild. Those values are combined into one total cost, so the code can rank candidate queries deterministically. This is a compact teaching score, not a replacement for backend-specific profiling. The visible output names the cheapest query, which helps show how validation metrics can also guide safer query selection. Finally, we want a clear yes-no gate that also tells callers why a query was blocked. This code turns the Lark AST checks into a small retrieval gate. A query that passes grammar validation can still exceed operational limits, so validate parses the text, transforms it with to-AST, and compares metrics against limits. The return value is intentionally actionable. It reports which budget failed instead of only saying the query is invalid. Here, the query is rejected because its wildcard score crosses the configured threshold, so retrieval would not be called. Tightening limits reduces backend risk, but may block more legitimate expert queries. The visible output shows the final decision and the first reason a user or caller can fix. This tiny pipeline maps directly to production ideas. Swap the grammar for your product language, turn the metrics into request-level budgets or per-user quotas, and use the gate to return helpful UI errors or suggest safer rewrites. The takeaway is short and practical. Parse first, make queries inspectable, and date before retrieval to avoid surprise load. Use this when you need predictable, pre-retrieval cost control. One caveat: conservative limits protect infrastructure, but can block expert queries, so tune against real usage. A practical next step is to tune the wildcard weight and clause cap against a representative production sample. Pick a week of real queries from your logs and adjust the wildcard cost and maximum clauses until the reject rate is acceptable, while peak load stays under your latency SLA. If short, practical IR helps, subscribe and watch the IR videos.